Hello, it's Frederick Amwa, and I'm here to talk about cache memory, associative mapping, and set associative mapping. So, without wasting much time, let's move on to cache memory. Basically, cache memory, when we talk of cache memory, are talking about storing frequently demanded things closer to those asking for it. So we are storing data close to the CPU so that frequently used data so that we can easily access it. And with a cache memory, we have an hierarchy of this. So with the memory, we have the CPU at the top, which has the registers stored in it. And the CPU has the registers. The registers, the registers are in the CPU. Now, when we talk of the memories that are not in a CPU, the first one is the cache memory. So after cache, sorry, but this is the cache memory, and we have the main memory, also known as the RAM. So you can just represent it by MM. So just write the main memory. Main, sorry, this is N. Then we also have the secondary storage and the tertiary storage. Now, talking about, okay, let me write secondary storage, SS, and the tertiary storage, TS. That will be TS. Now, moving from top to down, you notice that there's an increment in speed. Now, increment in speed in the extent that the tertiary storage is slower than the cache memory. So the cache memory is faster than the tertiary storage. And also the cost per bit is also high. The cache memory is more expensive than the tertiary storage. Now we have an arrow that also comes down, and when this arrow is coming down, we are talking about the latency or the bandwidth. The bandwidth has to do with the amount of data each of these memories can hold. And you know, the memories outside the CPU, but from the top, you know that the memory capacity increases as we move from top to down. The latency is the delay. So we move on to the memory capacities of the cache memory. Now the CPU registers the access type is the random type, and their memory capacity is in kilobyte. That's the registers. So kilobyte for registers. Kilobyte for registers. And the cache memory, which is our focus for this video, is measured in the megabyte, that is MB. Now as we move downwards, now there's a simple diagram that explains the cache memory. Let me put it. Now the first one is the CPU. Now the CPU is connected to the cache. And we have the main memory. Now what this means is that from the main memory to the cache, okay, let me bring the arrows here. From the main memory to the cache and vice versa, the transfer of data is slow. Now from the CPU to the cache, it is fast. And this explains the analogy that, or the fact that the closer a memory is to the CPU, the faster the memory responds. So programs are executed that are executed frequently are kept in the cache, as they are close to the CPU, and their time of execution is faster than the programs that are not executed frequently, which are kept in the main memory. So that explains why the cache memory is faster than the main memory. Now, we also move on to talk about the levels of the cache memory. So the cache memory is divided into three levels. So we have another diagram with the C. Yes, so we have L1, L2, L3, and the main memory, which we represented by MM. And this is our CPU. So what this diagram means is that the level 1 cache memory is closer to the CPU. So the level 1 cache memory is the fastest. So this will be the fastest amongst all of them. Now level 2 will be faster. And level 3 will be fast. But from the level 3 to the main memory is slow. Now, I should have mentioned this earlier, but it is important to note that cache memory was developed by Morris Welk. He's a British scientist in the year 1965. So there's an analogy that comes with the cache memory. The cache memory, we can use the analogy of a desk in a library, where I go to a library and I pick a couple of books that I'll be needing frequently. And as time goes on, I pack a set of books on my desk, and these are books that I have been using or I will be using frequently. Now, these books on my desk can be known as the cache memory. Now, if I want to access these books, I don't have to go all the way to the library because these books are closer to me. So that is the analogy of the cache memory and the memory, the CPU. So the cache memory, or the books that are on my desk, are representing the cache memory, and now they are closer to me. Accessing them will be faster than going all the way to the library. We also have other things that make use of the cache memory. We have the operating systems, the DNS, the data analysis, databases, the web browser, and the servers. All these make use of the cache memory. Now, when it comes to cache memory, we can talk of the cache eviction strategy, which is used when the cache memory is full. So when the cache memory is full, we talk of an eviction strategy that will allow us to get rid of some information from the cache memory. You also have the least recently used, the LRU. Now, the least frequently used are it returns the data that have been there for a while, that we have not been frequently for some time. These data are returned to the main memory. Now, we also have the random replacement. When the cache memory is full, it removes items randomly to free space for other items that will be coming into the cache memory. So basically, this is all about cache memory. We'll continue with the other sets. To the associative mapping, or the fully associative mapping. Now, associative mapping is a cache memory technique used to store data from the main memory. This method In this method, any block or main memory can be loaded on any line of the cache memory. So unlike direct mapping, where the blocks are directly linked to the lines of the cache memory, now in this associative method, there's no restrictions. We can link any block to any line at any time. So let's dive into that one. Now, with that, it uses what we call the content addressing memory. That will help us look for a memory. So when we have like a block of, let's say, 8 blocks, my 8th one is bigger. So block 1, block 2, and block 8. Now we have a cache memory of, we can store any, so this is block 1 to 8. And then binary wise, we are having the one that is 0 will be representing a 001. So let's choose block 4. Block 4, that will be giving us 011. Now you want to store 011 inside the cache. This is the cache. So the cache is empty, so you can store 011 into any of the lines. So line 1. Now, when it comes to the associative mapping, instead of using the offset, we are using the block index. So the block index becomes the tab. So it's a combination. So we don't use the offset again, unlike the direct mapping, to locate the cache, but we are using the block to locate the cache. Now, with this block, or with this main memory, we would have a PAS of 5. 1, 2, 3, 4, 5. And as you know, the last two is the offset. And the first three is the PA. Now this is the PA. Now this is what we are using to address the cache. So we are not locating any memory in the cache, but rather we are we are filling this block with the lines. Now, the key features. There are no fixed location for storing a block in a cache. Each cache line contains a data block, a tag, no identity which memory block is stored. When searching for a block, the system compares the tags of all cache lines simultaneously. So this requires hardware support. And how this works, the CPU generates a memory address. So the memory address comes from the CPU. Now the cache is searched for a machine tag. If a match is found, the cache hits, the data is retrieved. If not, cache miss, the block is brought from the main memory and placed in any free cache or replaces another if needed. Now, if the main memory gives us, the CPU gives us a binary number, and we look at the tag over here or the block index, and the block index can be found in a cache, we don't directly retrieve the data from the cache. But if the block index is not found in the cache, now the main memory will store information, or the main memory is placed in any free line in the cache. In this case, if we have another one that is 111, now if 111 is not found on the cache, when the main memory comes searching for 111, it will rather store 111 in the cache. Okay, so now we're going to talk about the set associative mapping. Now, the set associative mapping is a compromise between the direct mapping and the fully associative mapping used in cache memory. It divides the cache memory into several sets, and each set contains a fixed number of lines called ways. A block from main memory can be stored in any of the lines within a specific time. So just as we did for the associative mapping, we have a cache, let's say a cache memory over here, and we have the let me put the last one, that is the n, and we have the main memory over here. Pardon my lines. What this means is that with the associative mapping, the components of or the data within the main memory has already been transferred or has already been fixed on any of the lines over here. Now, any of the lines over here are divided into sets. So let's say we can divide a set to be given in any question on anything. So let's say we have three sets, that is set 0, set 1, and set 2. Now, what it means is that if this is directed to this, now the main memory directed to this line has other options, can be mapped to other lines over here within the same set. So the set has different mapping options. How this works, that the main address is divided into tags. That's the tag, the set number, and the offset block. Now the set number determines which set block maps to. Within that set, the block can go into any line. That is associative search within the set, and all the tags in the set are compared to find a match. So the tags in a set are compared to find a match. So if I'm finding a match, instead of visiting the whole cache memory, I'll be visiting the set. Let's say we are saying the tag is in set 0. That means I'll be limited. I'll just come into set 0 and look for it. Or let's say the tag is in set 2. I'll come into set 2 and look for it. And this gives out what we call the K-way mapping. The K-way mapping. So this is basically about the set summary about the set associative mapping.